Inverse matrices. Mathematics has identity elements. In addition, the identity element is 0. Because when 0 is added to a number, the original number is not changed. It keeps its identity. For example, if I had 7 and I added 0 to it, I still get 7. So 0 is the identity element for addition. In multiplication, the identity element is 1, because if I take 7 times 1, I still have 7. So in your prior work, you've encountered these identity elements before. When we come to matrices, it's a little more complicated. So let's take a look first at an inverse. Each number has an inverse number for addition, subtraction, and multiplication. Let's say we start with the value of 5. Okay, so if I start with 5, the additive inverse of 5 is -5, because when they're added together, you get 0, the identity element of addition. With multiplication, 5 is multiplied with 1/5. 1/5 is the multiplicative inverse of 5, because when you multiply together, you get 1, the identity element for multiplication. Matrices have identity matrices for multiplication. Now, square matrices have inverse matrices to go with them. There's no inverse matrix for anything other than a square matrix, and not all square matrices have an inverse. A matrix and its inverse matrix's product is an identity matrix. Now let's take a look at all that verbiage and how it applies. In this example, let's say I start with this first matrix. I'll call it A. Now the second matrix, when I multiply it with the first matrix, gives me an identity matrix. That tells me that the second matrix is the inverse matrix of my original. The -1 as an exponent indicates that it's the inverse matrix. So the very first matrix that we started with has the inverse matrix, and then when you multiply it together, you get the identity matrix. And that's what the symbolism up above says. If you start off with the square matrix and its inverse matrix, when you multiply them together, you get the identity matrix. So down below, we can say that the very first matrix and the second matrix are inverse matrices.